far, no technology problems today. It's kind of an exciting thing. Next thing you know, the Van de Graaff generator is going to work and life will be good. Okay, today we're going to be looking at Coulomb's law. And of course, we're going to be looking at the calculus aspects of Coulomb's law. So in 1785, Charles was Augustin de Coulomb. I'm going to ask somebody who speaks French natively, as well as, 5 other languages? How do you pronounce this? Hot soup? Or hot sauce, excuse me, I said it wrong. No, his whole name, the Charles Augustin de... Yeah, as you can see, I don't do it right. Thank you. So he came up with this law. What he was doing was very similar to what was done by Newton in determining that the force of gravity was an inverse square law. What Augustine did here, or August, yeah, that's not even how you pronounce it, right? What Coulomb, in English, did was he essentially took 2 globes and put charge on them and measured the force between them as he varied the charge and as he varied the separations. And by doing those experiments, he experimentally determined that the force was proportional to the product of the 2 charges and inversely proportional to the separation squared. Now, just like with gravitational force, it's the separation of the center of these globes. I have a slide coming up, just in a few slides, about Newton's synthesis. Of course, it has to be a few slides because I only have like 9 or 10. And Newton's synthesis is really important because what Newton did, remember, he's the one who invented calculus to begin with. He, using calculus, found that actually, let me just jump forward to that while I explain it, because it's kind of an important concept, except for it's 7 slides forward or something. Hi, Sally. Hi. Where's Newton's synthesis? I know it's here. I looked at it before class. Must be my... Okay, here's Newton's synthesis, the next to last slide. So Newton showed using calculus, and he did it for the gravitational force, but because the equation is exactly the same for the electric force as it is for gravitational force, his synthesis works for electric as well, that if you have a point charge or a point mass that is outside of a spherical uniform shell, then you can treat it as if all of the mass for gravity or all of the charge for electric is at the center of that sphere. Now, of course, that was the spherical shell, right, of negligible thickness. That means that any uniform sphere, that's any sphere where the charge density is only a function of radius, you could break it up into a whole bunch of spheres, each one being of negligible thickness, but a different charge density, and take the charge on each one of those little shells and say, okay, it's equivalent to that being at the center, and you end up with the result. As long as you have a uniform spherical distribution of charge, you can treat it as if all of the charge is at the center if you are outside of that charge. If you are inside, Newton's calculus showed that under the same conditions, the uniform distribution on a shell, it had no net effect on you. That is, think about the Earth. If the Earth was a hollow shell with nothing inside, and you were in here, so this is you, you're in this empty cavity, the force of gravity on the Earth, of the Earth acting on you would be 0. So you would be weightless anywhere inside of that shell. And if you go outside, so if you, instead of being inside, you move to being outside, let me change this so you don't see my pen selections. So if instead you're out here, then it would be exactly the same gravitational force as if all of the mass was at the center of the Earth. Does the idea here work for you? Now, of course, I'm not going to go through the calculus of this. It's not super long, but we don't have enough time to do every possible calculus derivation in the class. But you can kind of think about how it works. Let us suppose that you have a thin shell and you have an object here. And this thin shell has uniform charge distribution plus Q. And in here you have something with a charge of minus Q. Don't worry about capital versus lowercase. Technically, lowercase can move and capital can't. But nobody follows that technicality even. So I have this charge. Here, you're close to the charge. So what does that tell you about the strength of the force? It's going to be really large. Here, you're far from the force, so that force is going to be smaller. So you're going to have a force. Those two will make forces. This one here, positive and negative, is always what? Attractive or repulsive? Attractive. So I'm going to have a force that's pulling it like this and pulling it like this. This one here is pulling much harder than that one was. So if you just looked at those two, you'd say, well, you're going to have a lot more pulling you to the right than to the left. But you have to keep in mind, all of the charge to the right of that line is going to be pulling it to the right. All of the charge to the left of it is pulling it to the left. Where do you have more charge, pulling to the right or pulling to the left? You have more charge on the left side. So you have a smaller force between each piece, but this piece up here, of course, is pulling it up like that. Down here is pulling it like this. When you add up the horizontal parts, it ends up, and once again, you just have to use calculus for this, that you have an equal amount of force pulling to the left as you have pulling to the right. And likewise, up and down. You can always choose your line so one axis is going to be symmetrical, and you can say, well, by symmetry, the up and down have to cancel, and you only have to do one. So that's the essence of Newton's synthesis. So when we talked about what Coulomb did, notice, yeah, I had the two things here. I better put a box around that just so I'm consistent. When we talk about what Newton did, I think I want one too many, or Coulomb did. Coulomb was taking these globes and treating them as if the charge was right at the center, because Newton's synthesis had already been done to say that you could treat the charge as if it's at the center if it is following these rules. So, once he's done his work and he's realized, hey, this follows the same form, well, then that same rule is going to work. So I suppose when you start, you can't put it at the center. But after you're done, then you can put it at the center and be more precise. Now, I know this law, it's just an equation. It doesn't take a lot to swallow an equation. But if you look at it, there's a constant here and a constant here. Didn't mean to cut off on the minus sign. One is 1 over 4 pi epsilon sub 0. One is k, and I put a subscript of e on it to say this is the k for electric charge. This here is like bona fide constants. This here is what Coulomb found, right? Because Coulomb just found a constant that related the product of the charges and the separation squared. And then it's through a lot of theory that we find that these two are the same thing. So what is that epsilon 0 and what is the k? Epsilon 0 is called the permittivity of free space. It is a measurement that tells you about how much conductivity you have through a vacuum. Now, of course, you'd say, how much conductivity? Why, there's nothing in that vacuum. There should be no charge that passes through. But if you have a large enough difference in energy, you can make an electron break free and go through it. And so that's what this is measuring. So the subscript of 0 is what it means. That's what tells us it's free space. If it didn't have that subscript of 0, it could be going through something else, like, let's say urethane. Urethane's a really good insulator that we use in a lot of our wires. But the permittivity in urethane is about 2/3 or something like that, the permittivity in free space. So it's different. So that's just a constant. And if you take that constant, you can It's 1 over 4 pi times 10 to the minus 7. It's actually a really nice, simple number. And so you get this value, and it relates to k by the relationship we saw right here. 1 over 4 pi epsilon 0 is equal to k. I hope I did everything here right. Oh, yes. It relates with the speed of light squared. I was going to say, this here is actually mu sub 0, which is the permeability of free space. It tells you how magnetizable free space is. So the definition I used here is using another relationship. But it's a simple number. So when we look at these equations, they're equivalent. You'll see some textbooks, some references that use 1 over 4 pi epsilon 0. You'll see some that use k or k subscript e. You'll also find a few more advanced resources that drop this off completely. How could you make this constant equal to 1? There's something very simple that you have to do. Well, these are equal to each other, but how do we make that equal to 1? Okay, if we divide by it, what you have to do is you have to change your units. So there are some units that have been derived that are called natural units, I think, where they change the values so that the constant is 1, and that makes, of course, the calculations a lot simpler. But then we're no longer using the standard units, we're using a different set of units in that case. So when you see those, if you see that equation without the constant out there, it's just because they're using different units, ones that we will never talk about here. So I just mentioned this so when you see that, you don't wonder what's going on. Okay, already gone through that. We will, in just a moment, get to doing some problems. But first, we have to think about how we would do a problem. So, Coulomb's law tells us the force between 2 point charges. Well, what if we have a point charge and charge that's spread out over a large area? For instance, let us say that I have charge spread out all over the surface of this globe, and I want to find the force. Okay, Sally, there's new signs outside that say no food or drink in the classroom, so I need to be more careful now that we have signs of legislating this. I know. Okay, so let's suppose I want to find the force between this globe that has charge spread out over the surface and the corner of, I have some charge just on the corner here. Well, I can't conceivably just say, well, all the charge is at the center because this isn't uniform. It would be reasonably close, but it's not uniform. So, given that it's not uniform, I have to go ahead and add up the charge from each location. And so I have a vector for the force between this point and here, and a vector for between this point and here, and I would add up all of those vectors. Now we have to think back a little bit. How do you add vectors? Break them into components and add up those components. So we're going to need to go through some steps. So we add up all the force vectors from each piece, which is what we call an integral, and then we're going to have to, when we do those force vectors, we'll break them into components before we do the integral. So we'll do an integral for the x part and the y part and the z part, depending on the complexity, and do the x, y's, and z's separate. So here is what our Coulomb's law equation looks like. These are two exactly equivalent forms in the calculus form. What's really different here? Well, I just made one of the q's a DQ. It's a Dairy Queen. Let's all go get. Oh, the Dairy Queen's now a Chinese restaurant. Yeah, I guess we won't all go to the Dairy Queen and get ourselves a Blizzard. I don't know if you guys saw. You're probably not Facebook friends with Ken Osborne's wife. She's a pastor at a Lutheran church, and she had the marquee outside of her church said, "If you're praying for a blizzard, go to Dairy Queen." We'll have our services. It was pretty funny, I thought. Okay, so back to this. you have our constant K times the fixed charge times this thing here multiplied by dq, where dq is the charge on some small amount of area or volume, depending on the situation. Question from Michael.
How are they equivalent if the only difference I can really see is one is r squared and the other is r cubed?
The tops of the vector, and that's the key. Okay, so yeah, I was going to go over that, so you were right with me. So our vector has a magnitude of r and a direction of r hat, right? Because r hat by definition is a magnitude of 1 and just having the direction. And so if you were to substitute this into there, then one of the r's would cancel, and you'd have the r hat over r squared. I wrote it both ways because sometimes one form is more convenient and sometimes the other form is more convenient. So you always want to do your math in the most convenient form. I wrote it in both. Let's look at how we can do this. Oh, one more step. The DQs. We could have a one-dimensional problem, a two-dimensional problem, or a three-dimensional problem. For today, I'm only going to focus on the one-dimensional case, where I have charge spread out over a line. That line doesn't have to be a straight line. It can be a curved line. My first example is going to be charge spread out over a circle. So in that case, we use a charge per unit length, the lineal charge density, that is just the total charge divided by the total length. Has to be uniform for me to make this equation. Uniform means that that charge density doesn't change with location. So if the charge is uniformly distributed, I can just do it like that. If it's not uniformly distributed, well, I've got some more work to do. I'm going to have some more information. If it's two-dimensional, then you have the charge per unit area, and dq becomes the charge per unit area, dA. Three-dimensional dq is charge per unit volume. Notice we use rho again, just like we use for the mass density, dV. Okay, let's get on to it. First problem. We're going to look at the force on a point charge at the center of a circle of charge. So I drew a picture here. Obviously, it doesn't fit on the regular PowerPoint slide because I made it bigger. So I have that blue circle that has charge Q2 spread out uniformly all over it. And I have Q1, the charge at the center. I've defined my X and my Y directions. What do we do next? And you can be impertinent if you feel the need right now. Nobody's going to give me the impertinent answer? The don't waste your time answer? Do what? Well, this isn't a sphere, so that does, well, that doesn't technically apply here because it's not a sphere. But I have a symmetry here. And I can make a symmetry argument saying that for every possible, I'm going to change to a different layer here just so I don't screw things up worse than I have to. For every possible point like this point here, for which there's a force like that, there is a force on the opposite side, or a charge on the opposite side that makes a force of the same magnitude going the opposite direction. And so if I add those all up, it has to come up to 0. Right, so I know from the get-go the answer is going to be 0. So why do I do this problem? I'm doing it so we can see how to work a problem, even though we know what the answer is going to be. So let's go through the steps to work the problem. I have my system defined, nice picture. What's the first thing you think I should do? Okay, Tori is thinking about this very much. Like, if it's a test question, well, we've got the figure already. Next, we need our concept. So what is our concept here? That is not a truly rhetorical question, but pretty close. Right, truly rhetorical means I don't expect you to answer. It's close because you should all know the answer. What is our concept here? Almost heard an answer.
Coulomb's law.
Yes. So, find, what do I need to find? Okay, so there's written out what I need to do. I need to find, here's my equation. What do I need to fill in with that? Well, it's pretty clear what Q1 is. Q1 will just be that, right? Very simple. But what about DQ? What is DQ equal to?
Well, it's two-dimensional, so we can go back to that chart and look at what it should be, I guess.
Actually, while this is a two-dimensional figure, it's a one-dimensional charge distribution because the charge is only spread out over a line. It's not spread out over an area, right? So it's in a two-dimensional problem. And it seems odd to say, but it's a one-dimensional charge distribution if it's not a straight line. But it's one-dimensional if it's spread out over just a line, even if it's a curving line. So it's a one-dimensional, which makes it easier.
Lambda ds.
So dq is equal to lambda ds. And then I can say, well, from what we know, lambda, if it's uniform, because I said the charge was uniformly distributed, lambda is my total charge. What's the total charge on that circle? Not 0. Look at the picture. R. Q2, yes. Q2. And then what's the length of the circle?
R. Dot R.
We are definitely in Christmas mode. It's a circle.
So length 2R.
2 pi r. All right.
Oh, circumference.
Okay. So here we have lambda. We can calculate that straightforward. And so I can put this value into here, these two values into that equation, and I have df is equal to, I'm going to put the minus r hat here in front just together. Okay, q1, q2 over 2 pi r times ds over little r squared, where little r is the distance from the center to where the charge is. What is the distance from the center to where the charge is? Capital R. So I can also make a substitution, little r is equal to capital R, and make that a capital R squared. Now, if I didn't have that vector part in parentheses, this would be real simple, right? I would just integrate from 0 to 2 pi r and have my answer. But I have to add them as vectors, not as scalars. So the next step is to break this into components. And I didn't put that up above. But it's an important piece of the puzzle. So I break it into components. I've already defined my x and y directions. So let us say I have this angle theta here. Make life simple for me. And based on that angle theta, if my r hat vector is pointing along that line, then how much of the component is in the x direction? Right, how do we find the amount of this vector that has a magnitude of 1 if it's r hat that's in the horizontal direction? Yeah. So it's, in this case, it's 1 cosine theta. Right, 1 because it was the unit vector, not the total vector. Right, unit vectors always have magnitude 1. And then what about the value in the y direction? Oops. I started right, cosine. You are absolutely right, Jared. So there I have what r hat is in my Cartesian coordinates, and now I can break this up into components. So I will just say, dfx, notice I dropped off the vector sign because now I'm only talking about the x component, is equal to minus cosine theta, that's the minus r hat portion that's in the x direction, did I hear a question somewhere? No, okay. And dfy is equal to minus sine theta k q1 q2 over 2 pi r cubed ds. Okay, so now I've broken these up into components. What remains? What?
Doing the math, probably. I said doing the math.
Oh, doing the math. Now we're getting in the swing. Okay, doing the math. What would be a problem for doing this integral? Yeah, I have two variables. I have theta and s, both as variables. But we learned long ago that the arc length s is equal to theta r. So that means just take the derivative of both sides. ds must equal what? r d theta. So since there's an r on top and r cubed on bottom, I'm just going to make it over 2 pi r squared, capital R, d theta. So now I'm down to these rather simple beasts. And so now I have to integrate both of them. And I ran out of space, so I'm going to another page. So if I integrate these, let's put the constant stuff out front. Minus k q1 q2 over 2 pi r squared integral cosine theta d theta from 0 to 2 pi, because we go all the way around the circle. What's the integral of cosine theta going around a complete circle? I heard somebody say 0. And if we do likewise for y, And what's the integral of sine theta if we go over the complete circle? And so there we've worked it out going through the steps. We knew what the answer was going to be, so that part was trivial, but now we've gone through and we've applied the steps. That wasn't so trivial, right? Right. Okay. Now, a problem that you have on your calculus homework assignment. You have a calculus homework assignment entitled HWC1 that is due on February 16 or 15 or something like that. That assignment is exactly the assignment given, 8 years ago now, by the University of Nebraska Lincoln professor teaching electromagnetism the first day of class to make sure students learn what they're supposed to learn in this class. So I figure the homework assignment that he gives to make sure you learn what you're supposed to learn in this class is an appropriate assignment for me to give in this class. Make sure you understand the material. So that assignment is already available to you on Moodle, and the first problem is essentially what we're going to do for the rest of the class period. Now, when you look at that assignment, I want you to note that it specifies that you need to have careful drawings made with a ruler and so on. Right? Don't just sketch them. Draw the careful drawings as it indicates. I kept his wording and I'm grading it the way he would because I'm often, on some things I know I'm a little anal. On other things I'm really relaxed and let you get away with things I shouldn't. So I'm going with his level of what he requires for it's a sophomore physics class, but these days it's become a junior physics class because students don't come in with calculus, and I didn't come in with calculus either. They just said take it. Anyway, but it's the first class after this. So it's, what you expect to know. So let's look at this problem. Consider the force on a point charge Q1 due to charge Q2 evenly distributed over a straight wire of length L. Now, if you look at the homework, which Jared, I assume is going there, the first problem says that you have a semi-infinite wire. That's basically the difference between these two, and that it specifies much better where you're located. What does semi-infinite mean?
Kind of forever.
Kind of forever. That is a good literal interpretation. When you're talking about a line, a semi-infinite wire would be the same as if you're talking about a ray in geometry. It has a starting point and no ending point. So in that problem that's in your homework, you're going to be dealing with a wire that goes like this and never ends. Now for my problem here, I just said a wire of length L, so there's a difference. My wire ends and theirs doesn't. Now in the homework problem, there are two ways that it asks you to do it. Way number one says that I am going to find it's electric field instead of force. We haven't learned the words electric field. We'll learn them tomorrow in class, but it's the same calculation, so it's the same thing. The first one is for a point. I still have it in line mode. For a point directly above a distance B. So let's do this. The only difference fundamentally in what you're doing today and what you have in that first homework problem is mine is a finite length and that's a semi-infinite length. You had a question? Okay. So I have point charge Q1 here. And then I have charge of Q2 that is spread out over this length L. Now I'm not going to rewrite the concept because, we know it's Coulomb's law, and you are asked in that problem to lay out all of the different pieces of the concept as separate pieces. So I'm not going to go through the concept part. Let's just get right to it. What do I need to do to solve this thing? Tori is giving me the very broad yet absolutely true answers. Okay, so my equation is still going to be df is equal to minus r hat k q1 dq over r squared. Substitutions. What substitutions can I make?
Q1 is Q1.
Okay. Then what?
R is B.
No.
R is L.
No. You actually bit off the hardest of the three because you have to first define your coordinate system before you can actually answer this in its entirety. So where do you want to put your coordinate system? Where? Bottom. I am going to respectfully disagree with you. You could do that. It's not the easiest place, though.
Q1.
Okay, the easiest place is, let's put our coordinate system at Q1. Let's take this, rotate the picture by 90 degrees. It'll take me a step to rotate the picture because I didn't give myself enough space to rotate it. Move that over there. Oops, now I inverted it. No, I didn't. I'm good. Just get that to 90 degrees. Seriously. Okay. There, I rotated it. And now we'll just make our coordinate system so that I have and I found that I really have to do this in a funny way to make it even come close. I'm going to make my coordinate system go like, yeah. Okay, now, my picture's a little obliterated now. You can go back through the YouTube and watch the YouTube to see how it progressed to here. But now we can see this pretty simply. What is my value going to be for R now that I have rearranged things?
L over 2.
It's easier than that, my friend. R will just be X, because R is the distance from Q1 to where the charge is. And if I put my origin at Q1, then the distance X going from my origin to the charge I'm looking at is just R. Now let's draw a picture. I didn't draw this part on the last time. We're going to have a little piece of the wire here that we're looking at. That little piece has width of ds, right? And the charge contained is dq is equal to, and we haven't said it yet, but it should be lambda ds. Well, what is lambda? Okay, which q? Q2 over L. The total charge divided by the total length. So I have that. What about ds? This goes in with the r equals x. If I go along that line, what is ds actually equal to with my coordinate system? Dx. So ds is just dx. So now I have all my substitutions in violet or magenta. I'm sorry, you can't see. And so let's put those substitutions in. Notice I have a vector equation. It's only one-dimensional. Is there a point in keeping a vector equation for a one-dimensional problem? No. So I'm going to drop this off and just say df sub x equals, and what direction? Assume, if you're not given signs, assume Q1 and Q2 are both positive. If they're negative, that's going to reverse the direction. So if these are both positive, what direction should the force be from any piece of that wire on my charge? It should be in the minus x direction. So I'm just using plus will be the positive x direction, minus will be the negative x direction. So it should have a minus here. So I didn't even pay attention to the fact that this had minus r hat. I just used my noggin to say what direction is that force going to be if likes repel. So I have minus k q1 q2 over L, and then I'm going to have dx over x squared. Right, the q2 over L was lambda. I'm going to rewrite it so it's clearer how I put these pieces together. Nice job. Okay, anyone question how we got there?
So the negative r hat just becomes a negative 1 essentially.
Well, that was it. The negative r hat was telling me it's in the direction opposite of going from Q1 to Q2. So I could have looked at here and said, okay, going from Q1 to Q2 was going this way. So it's minus that direction, so it's going that way. But what I did, instead of doing it very dogmatically like that, I just used my rule that opposites repel and said, well, the force between a positive Q2 and a positive Q1 is going to be repulsive, so it's going to be this direction. And that was doing exactly the same work, but instead of doing it mathematically without thinking about the reasons, I was doing it with the reasons, not paying much attention to the math. So it is the substitution like you said. Yes is the answer. But I want to make sure I gave the reason why. All right. Now that we have this, there is only one step remaining. What's that one step? Integrate. So let's put the constants out front again. What is my starting and ending limits for this integral? What are? There's two of them. Not 0. Where does the wire start? B. So the lower limit is B. That's the minimum x. What's the upper limit? B plus L. Okay, now we just do the integral. What's the integral of dx over x squared?
Negative 2x and negative 3.
Okay, when it's the integral, you divide by the new power. So the new power is going to be minus 1. Right?
Right.
1 over x squared is equal to x to the minus 2. So I raise the power by 1, which makes it x to the minus 1. And then I divide by that new power, so I divide by minus 1, which means it's negative 1 over x. And now, of course, by this point, going through a semester of physics, the whole limit thing should be getting a lot more comfortable to you. You know, as a physicist, calculus always has limits. I was talking to Lisa, and we don't use limits all that often because she's more interested in the theory of doing the calculus and not the practical application. So we put in these limits. Now notice I have a minus and a minus. So I'm going to go ahead and make this a positive. K Q1 Q2 over L. And then put in the upper limit, 1 over b plus L, minus the lower limit, 1 over b. What do you do now?
Find a common denominator, I guess.
That's right, Michael. Find the common denominator. So the simple way of finding the common denominator is, well, these aren't factorable anyway, right? So we're just multiplying this by b over b and this by b plus L over b plus L. Right, there I have a common denominator. B minus b plus L. The b subtract out and I'm left with a minus L on top. So that's equal to notice these L's now cancel. Minus sign comes out again. That by out I mean out front. Now, I'm guessing you wouldn't have come up with that answer right off the bat looking at the problem. But going through each step, we can see the logic that builds to getting this equation for the force in the x direction. I didn't do the force in the y direction. What would the force in the y direction have been?
0.
0. Right. That's why I didn't do it. It was a one-dimensional problem. Now, I see from the time I don't have time to complete this, but I am going to start it because problem 1b, your homework assignment has, I don't know, 6 or 7 problems, but the problems have like parts A, B, C, D, E, F, G, H, I. Yeah, I know. It reminds me of the back to school. I have only one problem in 27 parts. So now instead of having the charge above, we have it to the side. Now for your problem, A is 0. It's not offset at all. And your problem, it's again semi-infinite, goes on to infinity. The method would be the same. I just changed it up a little so we could look at things differently. The key to doing this, you'll find your df, and you'll have to say, okay, well, let's say I'm looking at this little piece, ds here. That ds, of course, is going to be dy. So I'll have ds is equal to dy. Let me change to magenta like I did before. And I will have the radius, the distance separating my charges is r, where r is, using the Pythagorean theorem, r squared is x squared plus y squared. But of course, I know one of those variables, since it's always an x distance of b away, I can replace this with r squared is equal to b squared plus y squared. What was your question, Tori?
Oh, so just going to confirm that Q1 is at the origin.
Yes, Q1 is at the origin. My coordinate system obliterated it. So I have my ds, and I know that r squared is b squared plus y squared. What I'm going to want to do is to find the equation for my force. Actually, I'm going to leave it in blue. My force is equal to minus k q1 lambda ds over r squared, right? And then we have the r hat that I didn't put here. Break that into components.
Supposed to be df?
Excuse me?
Supposed to be df?
Oh, yes. Yes, it is. And a vector sign. See, I'm trying to hurry because you're standing up. I have 1 minute left. So having this equation, I break it into my x and y components. dfx is equal to the magnitude of df cosine theta, and dfy is equal to the magnitude of df times sine theta, just like we did before. But here, it turns out that the prudent way to solve the problem is not going to be, well, it's going to be to make theta your variable. And so, of course, there's no theta in here. I had the ds. And so what I need to do is find a relationship between my ds, which is dy, and d theta. And the way to do that is I define sine, cosine, tangent. If you take this tangent and take the derivative thereof, and I put the derivative of tangent because I don't have that memorized and I want to be able to do this in class, then I get the equation that says d theta over cosine squared theta is equal to, notice the other side was y over x, where x is a constant, x is just b. And so that's going to be dy over b. So now I can replace dy is equal to b d theta over cosine squared theta, and I can put that in for my ds. And now I will have things in terms of theta, and you may or may not, depending on your problems, have to do some conversion of r into b squared and y squared. But then you're ready to solve the problem. So it's this step of converting variables that is the tricky part on this that I want to make sure I cover. Because you are not going to do part B of that homework problem 1 part B without using this conversion of variables into theta. Okay, we are out of time.